Welcome everyone to week 3 of heat and thermodynamics. This week we're going to break it into two different parts, and the first part is really just kind of the intermediate step to the last piece of this part. So last week we had you going through and drawing maps and determining how many different cues there are per phase change and how to draw those maps, and that was the last part. Now today's lesson is really just going to look at one or two of the cues of a particular map. So I'm going to assume you can draw maps with the arrows, and we're just going to kind of like, hey, what's the Q2 then, or what's the Q3, and kind of going through and looking at it that way. And then from in part 2, then we'll kind of do it all, put all the pieces together. So that's kind of where we're heading. So let's take a look at the notes for this week. All right, so I'm calling this steps in temperature and phase change, and the reason I'm calling it steps is we're going to look at each individual kind of step along the way and look at it, so that's why. So just a quick review, when we draw these maps, what we're going to do is we are going to be putting our temps and Q's or heat on each, the X and the Y axis, and what we do is we put our minimum temp and we put our maximum, and if there happens to be a phase change, we put a dashed line at the phase change, and then we go through and we put a minimum, the minimum temperature, we put it out of the maximum, and then we get a temperature change, we get a phase change, and we get a temperature change, and we draw arrows from our initial to our final. This is where Q was gained. And the reason we know it was gained is because it went up into the right. So same thing here. We have our maximum temp. We have our minimum temp. We have a phase change that occurs along the way. But this time when we go through and we say this is where it starts and this is where it stops, now what happens is we have this a Q, and a Q. So that's what this, now they look maybe similar, but now what we're doing is we're starting with heat here and we are losing heat. So Q is lost in this example. Now what today, part 2 of last week was really focusing on how many Q's do you have. I'm going to change colors there. So the way I have it drawn is we start here. So I'm going to label that my Q1. I'm going to label this Q2, and I'm going to label this Q3. And over here, we started here, and we went down, so I'm going to call this my Q1, this my Q2, and this my Q3. Now, really, those 1s, 2s, and 3s are arbitrary. We can define them really any ways we want. We could call this 1, and we could call this 3. It's fine. But the idea is if we start here and we end here, it just kind of makes sense to number 1, 2, 3. But it ultimately, what we're getting to for part 2 is we're going to be summing up all the Q's for this. So we're going to be going through and we're going to be taking Q1 and Q2 and Q3 and we're going to be putting them all together. So this is just kind of quick review on how to draw the maps. This is from last week's slides. It's a screenshot. It's exactly what you should probably have already in your notes as a review on how you draw those maps. And that's not going to be the focus of this lesson. In part 2, you will be required to draw these, so don't forget about how to draw these maps. Again, what's the difference between latent heat diffusion versus vaporization? Are we going from solid to liquid or liquid to gas? That's kind of the idea. Gain positive and negative, and it's the direction. So this is all just review stuff for this. So here's a map. So this particular problem, if we have 5 kilograms of water, starts at 40 degrees Celsius and it ends at 90 degrees Celsius. So I drew the map for you. And in this particular map, because I identified that it was water, and I looked and said, hey, look, the boiling point is 100 and the melting point is 0. No phase change is going to occur. So in this situation, there was only one Q. So now what I'm asking you to do is, what does Q1 equal? So what we have to decide, is it a temperature change, right? A temperature change, or is it a phase change? So this is the equation we're going to use. If it's a temp change, this is the one if it's a phase change. Okay, so in this case, my line's going up. That shows that my temperature is changing. So therefore, we're going to use the temperature change one. So then it's simply Q is equal to MC delta T. Now don't forget delta T is final temperature minus your initial. So when we go through and we solve for Q, we've identified this water, and at 40 to 90 degrees, it is liquid water, not ice. So then we can say Q is equal to 5 times the specific heat of water, 4,186, times my change in temperature. My final temperature, it started here and it ended here. In liquid water, this is all, I'm only talking about, this is my Q1. I should have added that. This is my Q1. Is my final temperature, and this is my final, and this was my initial, and we have the initial, and we have it going in this direction. So this is going to be my final temperature of 90 minus 40. So that's going to be a positive 50 then, right? So did this gain or lose heat? It's going to gain heat. The temperature increased, so it gained heat. So my Q1 is going to equal 1,046,500 joules. Okay, so it's a temperature change and a temperature change only. So that's what that looks like. Now, where does all this stuff come from? It's a reference, it's tables. I'm just putting it very conveniently on the bottom of your slide. On your homework, you'll have to look at a table like this to determine melting points and boiling points of the individual substances. And then you will also have to look at something like this to look at what are those values of the specific heats, where on the previous one, these are the latent heat effusions versus vaporization. So these are tables that you have to reference. And the idea is, oh, I'm looking at ethanol, so I'm looking at this column, or I am looking at lead, so therefore I'm looking at this row. Pardon me, I said column, I meant row. So these are just tables, and I have no expectations for memorization of any of this. So here's another example. We have 3.2 kilograms of liquid aluminum that starts at 700 degrees. So I drew my map. So it starts up at, I drew my largest temperature, I drew my smallest temperature, 720. And then we can go through, well, was there a phase change that occurs? Well, we know that the melting point and freezing point of aluminum is at 660. So yes, there was a phase change, and that phase change occurs right here. So I draw my dashed line, and then it starts up here. So I go down, over, down. That's the drawing of the map. I'm just showing you what it is. In this particular problem, I'm just asking, what is Q3 equal to? So what is that? So we have to say, well, is it a temp change? Is it a temp change at Q3, or is it a phase change? And I hope you realize that because this temperature, the line is changing, that's a pretty good indicator that it's going to be the temp change. And that's exactly what this is. So I'm only looking at Q3, and I want to draw your attention to something, that when we talk about Q3, we are only talking about that. We are ignoring Q1 and Q2. We are focusing on Q3 and Q3 only. So Q3 is aluminum. So it's a temperature change. So Q3 is equal to MC delta T. So we can go through and say Q3 is equal to the mass, which is 3.2 times the specific heat. Now, we know it's aluminum. So this is our temperatures that we go through the phase change, and I only know the specific heat of aluminum. Now, just to set the record clear, this is of solid aluminum. So really the only numbers that we know of the gas, the specific heat values we know of gases, is gas in the water in the gas phase, called steam or water vapor, and we know the specific heat of solid water, which is called ice. So conveniently, I chose Q3 to be the temperature change because this is going to be the specific heat we're going to use. It's solid aluminum, and this is in the solid form at that point. So we're going to use that 899. So we're going to use 899 as my specific heat. Now, I very specifically circled the points in which it starts and stops, because the reason for that is I'm only looking at my temperature changes between those two red lines that I just drew. From sorry about that. I don't know what just happened. Everything just disappeared. So we are very specifically talking about the Q3 between that. So we're saying Q3 is equal to MC delta T. So Q3 is equal to my mass of aluminum times, we had said, the specific heat times my change in temperature. So from right here, we have to say this is my starting or my initial, and this is my final. So this is the temperature it starts at, Q3 starts at, this is my temperature that Q3 ends at. So remember, final minus initial. So my final temperature is 20 minus my initial temperature of 660.4. Now, hopefully you realize that 20 minus 660 is going to be a negative number, which means overall my Q3 is also going to be a negative number, which is an indicator that it's losing heat. So my overall value is negative 1,842,302.72 joules. Okay, it lost heat, therefore it's going to be that negative number. But we're only looking at that Q3, so that's the temperatures we're using there. So let's give this, I'm going to have you try this one on your own. So we have water, and it starts at negative 20, and it goes up to 15. And I'm asking you, what is Q1? So pause this, solve for Q1. You're going to have to figure out, is it a temp change or is it a phase change? And if so, which one it is, plug it in, solve for Q1. So go ahead and unpause when you got it. Okay, so hopefully you realized that this is definitely going to be a temperature change. So Q1 is equal to MC delta T. So when we look at Q1, we're going to say, well, Q1 is equal to the mass of 4.2 times my specific heat. Now, this value, your overall answer, is not 263,718 joules. It is not. And here's the reason, is when we look at this, it's water, right? So it's water, but also ice is water. It's just ice in the solid form. There's water in the solid form. So we have to decide between negative 20 degrees and 0 degrees, is it ice or is it water? And it's ice. So this is 2090 for a specific heat value. And then we're going to go through and we're going to take our final minus our initial temperature. So my final temperature is right here. My initial temperature is right here. So it's going to be 0 minus a negative 20. Now, 0 minus a minus 20 is positive 20. So when you go through and you do this calculation, we're going to get a Q1, and hopefully you got this, of 175,560 joules. It's a positive number because it gains heat, and it's the specific heat of 2090 because it's ice. It's water in the solid form. So we had to choose that. Now, notice this is it's only from here to here, so it's 0 minus a negative 20, and it's only talking about Q1. It's not talking about from beginning. It's not talking about from the beginning all the way to the end. It's only talking about Q1. Last problem, you try this one on your own. Hit pause, 2 kilograms of water at 120 degrees, ends at 85 degrees Celsius. What is Q2 equal? Hit pause, unpause it when you got it. So Q2, we are only looking at Q2. So this is water, and it starts at 120 degrees. It started up here, which is above the boiling point. So we had our phase change. That's what that dotted line represents. And then once it gets to the phase change, it's going to dip in temperature change. So you hopefully recognize that this is a phase change. So Q is equal to plus or minus M times L. And then you have to decide which L is it. And this has been a little bit since we've talked about this. So is boiling point latent heat of fusion or latent heat of vaporization, and these two go together, and these two go together. Okay, so this is latent heat of vaporization. We're vaporizing water, right? Like the water vapor. So it's going to be latent heat of fusion. So this is going to be latent heat of latent heat of vaporization. And now we have to decide, is it the positive or the negative? And because it's going from the upper left, it's losing heat. It's going from 120 to 85. We are losing. This is going to be a negative. So my Q is going to be a negative mass of 2 times the latent heat of vaporization of 2,260,000. So I should have been calling this Q2 the whole time. So Q2 is equal to negative 4,520,000 joules. Okay, so that's all the first part is going to be, is I'm going to go through, I'm going to set up a problem, and I'm going to ask you to solve for one of the Q's given a map that you have to go. And you're going to have to figure out, is it a phase change or a temperature change, and is it a positive or negative? And that's part one. When you're done with the homework sheet, then you're going to go through and take the quiz just like last week. Have a great day. Let me know if you have any questions via email or office hours.